constant K in the voltage drop equation is defined as the resistivity of the conductor times the length of the conductor divided by the cross-sectional area of the conductor. The resistivity of copper is 1.7241 times 10 to the negative 8 ohms meters. The length is in meters and the area is the cross-sectional area of the conductor in square meters. For a standard distance of 1000 feet, which is 305 meters, and a conductor with a cross-sectional area of 1000 circular miles, which is 5.7 times 10 to the negative 6 square meters, the K value for copper becomes 1.7241 times 10 to the negative 8 ohms meters times 305 meters, divided by 5.7 times 10 to the negative 6 meters squared, which equals 12.9 ohms per kc mil. The voltage drop equation is voltage drop equals K times I times L, where voltage drop is the voltage drop in volts, K is the constant 12.9 ohms per kc mil for copper, I is the current in amps, and L is the length of the conductor in 1000s of feet. The National Electrical Code, NEC, allows a maximum voltage drop of 3% for branch circuits and 5% for feeders. For a branch circuit, this means that the voltage at the load end of the circuit cannot be more than 3% lower than the voltage at the source end. Starting with a higher voltage at the source does not provide any additional room for voltage drop. The allowable voltage drop is still 3%. If the voltage at the load end drops below the minimum allowable voltage, 116.4 volts for a 120 volts circuit, then the circuit will not operate properly. Therefore, it is not possible to start with a higher voltage and still maintain the allowable voltage drop. The voltage at the source must be within the allowable range to ensure that the voltage at the load end meets the minimum requirements. In more detail, let's examine the voltage drop calculation and the implications of exceeding allowable limits, as well as the concept of voltage variation at the source. The voltage drop is the reduction in voltage that occurs as electricity flows through a conductor. This is due to the resistance of the conductor, which impedes the flow of current and converts some of the electrical energy into heat. The voltage drop is directly proportional to the current flowing through the conductor, the length of the conductor, and the resistance of the conductor. The formula for voltage drop is voltage drop equals I times R, where I is the current in amps and R is the resistance in ohms. The National Electrical Code provides guidelines for the maximum allowable voltage drop in electrical circuits to ensure efficient and safe operation of electrical equipment. For branch circuits, which supply power to individual loads such as lights and appliances, the NEC recommends a maximum voltage drop of 3%. For feeders, which supply power to branch circuits, the NEC recommends a maximum voltage drop of 5%. These limits are in place to prevent equipment malfunction, overheating, and other potential hazards that can arise from excessive voltage drop. Now let's talk about why starting with a higher voltage does not necessarily solve the voltage drop problem. While it might seem intuitive to increase the source voltage to compensate for voltage drop, this approach is not always practical or effective. The reason is that electrical equipment is designed to operate within a specific voltage range. Exceeding this range can damage the equipment or cause it to malfunction. For example, if an appliance is designed to operate at 120 volts, supplying it with 124 volts could shorten its lifespan or cause it to overheat. Moreover, increasing the source voltage does not change the amount of voltage drop in the circuit. The voltage drop is still determined by the current, length, and resistance of the conductor. If the voltage drop exceeds the allowable limit, increasing the source voltage will only raise the voltage at the load end by the same amount. For instance, if the allowable voltage drop is 3% and the source voltage is 120 volts, the minimum voltage at the load end should be 116.4 volts. If the voltage drop exceeds 3%, increasing the source voltage will not bring the load end voltage back within the acceptable range. There are several methods to mitigate voltage drop in electrical circuits. Firstly, increasing the conductor size reduces the resistance of the conductor, which in turn reduces the voltage drop. Secondly, shortening the length of the conductor also reduces the voltage drop, as the voltage drop is directly proportional to the length. Thirdly, Using conductors with low resistance materials, such as copper or aluminum, minimizes the voltage drop. Fourthly, reducing the current flowing through the conductor by using more efficient equipment or reducing the load also decreases the voltage drop. In practice, electrical designers consider these factors when designing electrical circuits to ensure that the voltage drop remains within acceptable limits. The NEC provides tables and guidelines for selecting the appropriate conductor size and type based on the load, distance, and allowable voltage drop. Furthermore, it's important to consider the cumulative effect of voltage drop in long circuits or systems with multiple loads. The voltage drop in each section of the circuit adds up, and the total voltage drop should not exceed the allowable limit. Electrical engineers use voltage drop calculations to determine the optimal conductor size and configuration to minimize voltage drop and ensure that all equipment receives the proper voltage. Now, let's consider a scenario where a person starts with 124 volts at the source and experiences a voltage drop to 116 volts at the load end. At first glance, this might seem acceptable because the voltage at the load end is within the range of 116 volts to 124 volts. However, this scenario violates the NEC recommendation of a maximum voltage drop of 3% for branch circuits. To illustrate, if the source voltage is 124 volts, the allowable voltage drop is 3% of 124 volts, which is 3.72 volts. Therefore, the minimum voltage at the load end should be 124 volts minus 3.72 volts, which is 120.28 volts. In the given scenario, the voltage at the load end is 116 volts, which is 8 volts lower than the source voltage of 124 volts. This represents a voltage drop of 6.45%, which exceeds the allowable limit of 3%. As a result, the circuit may not operate properly, and the equipment may be at risk of damage or malfunction. To rectify this situation, the conductor size should be increased or the circuit length should be shortened to reduce the voltage drop. Additionally, the source voltage should be adjusted to ensure that it falls within the acceptable range for the equipment being supplied. Let us dive into the mathematical relationships and the practical implications for electrical installations. The K factor, often encountered in voltage drop calculations, represents the resistance of a specific conductor material per unit length and cross-sectional area. Its derivation is rooted in Ohm's law and the material properties of conductors. Understanding the K factor is crucial for accurately predicting voltage drop in electrical circuits. Firstly, we need to understand the fundamental relationship between voltage, current, and resistance as described by Ohm's law, which states that voltage equals current times resistance. In the context of a conductor, resistance is influenced by the material's resistivity, length, and cross-sectional area. Resistivity, denoted by the Greek letter ρ, is a material property that quantifies its opposition to the flow of electric current. Copper, commonly used in electrical wiring, has a relatively low resistivity, making it an efficient conductor. The length of the conductor directly affects its resistance. A longer conductor offers more opposition to current flow compared to a shorter one. Cross-sectional area, which is the area of the conductor's cross-section perpendicular to the direction of current flow, also influences resistance. A larger cross-sectional area provides more space for current to flow, reducing resistance. Mathematically, the resistance of a conductor can be expressed as resistance equals resistivity times length divided by area. The K factor is essentially a simplified way of representing the combined effect of resistivity, length, and cross-sectional area for a specific conductor material. The formula for the K factor is K equals resistivity times length divided by area. In this formula, length is typically expressed in feet, and area is expressed in circular miles, which is a unit of area commonly used in the electrical industry. When calculating voltage drop, we use the formula voltage drop equals K times current times length. Here, voltage drop represents the decrease in voltage from the source to the load. Current is the amount of electrical current flowing through the conductor, and length is the length of the conductor in feet. By knowing the K factor for a particular conductor material, along with the current and length of the conductor, we can easily calculate the voltage drop. It is important to note that the K-factor varies depending on the conductor material and the units used for length and area. For example, the K-factor for copper is different from the K-factor for aluminum due to their different resistivities. Similarly, the K-factor will change if length is expressed in meters instead of feet, or if area is expressed in square inches instead of circular mils. Now let's consider a practical example to illustrate the use of the K-factor in voltage drop calculations. Suppose we have a copper conductor with a K-factor of 12.9 ohms per circular mil foot. The conductor is 100 feet long and carries a current of 20 amps. Using the voltage drop formula, we can calculate the voltage drop as voltage drop equals 12.9 times 20 times 100, which equals 25,800 millivolts, or 25.8 volts. This means that the voltage at the load end of the conductor will be 25.8 volts lower than the voltage at the source end. The allowable voltage drop in electrical circuits is specified by the National Electrical Code to ensure safe and efficient operation of electrical equipment. Exceeding the allowable voltage drop can lead to various problems, including reduced equipment performance, overheating, and even equipment failure. For branch circuits, which supply power to individual loads, the NEC recommends a maximum voltage drop of 3%. For feeders, which supply power to branch circuits, the NEC recommends a maximum voltage drop of 5%. These limits are in place to minimize the negative effects of voltage drop on electrical equipment. When designing electrical circuits, it is important to consider the allowable voltage drop and select conductors that are appropriately sized to minimize voltage drop. The NEC provides tables and guidelines for selecting conductor sizes based on the load, distance, and allowable voltage drop. By following these guidelines, electrical designers can ensure that voltage drop remains within acceptable limits and that electrical equipment operates safely and efficiently. In addition to selecting appropriate conductor sizes, there are other methods to mitigate voltage drop in electrical circuits. One method is to shorten the length of the conductor, as voltage drop is directly proportional to length. Another method is to use conductors with lower resistance materials such as copper or aluminum. Finally, reducing the current flowing through the conductor by using more efficient equipment or reducing the load can also decrease voltage drop. Now let's discuss the concept of varying voltage at the source and its implications for voltage drop. While it might seem like increasing the source voltage could compensate for voltage drop, this approach is not always practical or effective. Electrical equipment is designed to operate within a specific voltage range, and exceeding this range can damage the equipment or cause it to malfunction. Moreover, increasing the source voltage does not change the amount of voltage drop in the circuit. The voltage drop is still determined by the current, length, and resistance of the conductor. If the voltage drop exceeds the allowable limit, increasing the source voltage will only raise the voltage at the load end by the same amount. Therefore, it is important to address the root cause of the voltage drop by selecting appropriate conductor sizes, shortening conductor lengths, or reducing current flow. In some cases, it may be necessary to install voltage regulators to maintain a stable voltage at the load end, especially in long circuits or systems with fluctuating loads. Voltage regulators are devices that automatically adjust the voltage to compensate for voltage drop, ensuring that electrical equipment receives the proper voltage. In summary, understanding the K-factor, voltage drop calculations, and allowable voltage drop limits is essential for designing and installing safe and efficient electrical circuits. By carefully considering these factors, electrical designers can minimize voltage drop and ensure that electrical equipment operates reliably and safely. The K-factor simplifies voltage drop calculations, the NEC provides guidelines for allowable voltage drop, and various methods are available to mitigate voltage drop in electrical circuits. Voltage variations at the source must be managed carefully to avoid damaging electrical equipment.